Okay, let's get going. So this is 5.2 GI Autoimmunity. We're going to be talking about type 1 diabetes mellitus as well as celiac disease. So what is type 1 diabetes? Well, that's destruction of pancreatic beta cells within the islets of Langerhans, or you might also see the pancreatic islets. So these are basically the endocrine islands within pancreatic tissue. Okay, so we knock out those beta cells, which are the sole producers of something called insulin, which is a hormone that helps regulate my blood glucose. Specifically, it helps lower blood glucose. Blood glucose. Okay, good arrows. So chronic hyperglycemia will follow, and dependence on exogenous insulin is mandatory. Obviously, if this is not maintainable. This is something that will need intervention at some point. So we need to have some sort of insulin pumped in or injected at some point. But what is normally occurring here? The normal anatomy and function. So the pancreas contains both exocrine and endocrine tissue. Let's go on over to this drawing that I have here. So this is how your pancreas looks. It looks like a chicken tender. 99% of the tissue that composes the pancreas is exogenous. Or I'm sorry, is exocrine. Exocrine. Which means it secretes into the organ's own ductwork. In this case, the exocrine products secreted into the pancreatic ductwork are digestive enzymes. They're going to run through this whole main pancreatic duct, and then they dump into the duodenum, and that's where all of my food is, right? The stomach is right here. And then the small intestine is down here. So that's where all the food is running. So all the enzymes that the pancreas makes get dumped in here, and that is its exocrine function. Okay? Its endocrine function is more so composed of little islands of tissue, and these are those pancreatic islets, or those islets of Langerhans. Whoops. And these are endocrine, which means secreted into the blood. Body-wide. So you see how that's a bit different from into the organ's own ductwork rather than going absolutely everywhere. That's what makes the endocrine system so powerful, is that it's the secretion of hormones, and hormones go absolutely body-wide and have very powerful effects. In this case, it's no different. These cells, or these islets, house cells that produce insulin, glucagon, and somatostatin. Let's look at those real quick. So your beta cells, insulin secretion, lower blood glucose. Glucagon from the alpha cells, raise blood glucose. And somatostatin, this is like the lesser known sibling. This is what is it? This is the Kevin of the Jonas Brothers. It regulates metabolism. Yeah, but we're not really concerned about that. We're concerned about blood sugar maintenance. So the way insulin works is it tells my cells to upregulate a glucose door, basically, to send that insulin that's in the blood into my cells, thus lowering blood glucose, if that makes sense. So, very crucial in determining if my cells are getting sugars, carbohydrates, or not. These islets are richly vascularized, which makes them really accessible so they can send out their endocrine products, but it also means they are accessible to the white blood cells, to the immune system. Okay? So again, we're talking about the disease. We're talking about wiping out the beta cells. What leads to that? There's a genetic susceptibility, a strong association with some HLA genes and some non-HLA genes. So this goes to the point of HLA codes for MHC complexes, which are the platters for antigen presentation. So little tweaks in that can maybe affect how these cells deal with self-antigens. So maybe some HLA combos are more apt to present you than other HLA combos are. All right, so this is the case. However, it's not the full story. You can have a quote-unquote bad HLA combo and not develop any type of autoimmune condition. There's other factors at play here. Concordance in twins is only 50%, which I find really interesting. And I know I say it a lot in this class, but genetics and environment both have a play, nature and nurture. Environmental triggers, and this is a great example of this, infection, right? We've seen how stressful a full-on infection can be for the body and for the immune system, and how many things have to go right for proper defense to be handled. So we can have accidental molecular mimicry here that might produce a response when maybe an antigen or some sort of bacterial peptide or whatever looks like a pancreatic molecule that can potentially lead to this diabetic reaction. But again, there's a lot of this stuff is up in the air. Also, your diet and microbiome composition can play a role. This is less. I know less about this, but I did see this in my research. All right. Autoimmune activation. So what happens here? Your antigen-presenting cells in the pancreas bind and present beta cell antigens, right? They're not really antigens. They're quote-unquote antigens. Your immune system has just confused stimuli for whatever reason, be it a genetic reason or an environmental reason, or usually both. And now the CD8 T cells are going to target and get rid of the beta cells. And you are forming a full immune response. So the CD8 T cells will have the CD4 T cells helping orchestrate things, also leading to the activation of B cells that secrete autoantibodies against beta cells. So a whole-on, full-force immune eradication of your insulin-producing cells. Very, very not good here. Be sure to know the difference between a B cell and a beta cell. I know. Biology is so fun and confusing. That is your antibody factory. Beta cell is your insulin factory. Okay. So what are the treatments? Like I said, you can't live without insulin. This is a really fundamental hormone for metabolism. If you can't break down carbohydrates, you are going to be struggling for proper energy production. So we need a regimented insulin injection or an insulin pump. Those can be surgically inserted and dose out insulin at regimented intervals. These folks would obviously just have to regulate their diet carbohydrate-wise. Exercise has been shown to increase insulin sensitivity, so this can be another method. But remember how I kind of started with autoimmunity. If you yourself are the stimulus, then true cure is almost impossible here. And this is the case. We can mitigate this disease arc, but at the end of the day, there's nothing we can do to make more beta cells, at least at this point in science. So we need to have some sort of exogenous insulin to ensure proper metabolism occurs. The big thing here is we want to prevent DKA. That is diabetic ketoacidosis. If I can't get glucose into my cells, then I have to switch to breaking down fats. Fat metabolism produces something called ketone bodies. Ketone functional group is just that double-bonded oxygen to other groups. And those are highly likely to produce a acid. Okay? If you want to know why, go take organic chemistry, because I can't recall why. But it does produce acids and can lead to something called metabolic acidosis. So you are dropping pH body-wide. Not good for a variety of chemical reactions. So we really want to avoid that, which is why we need this insulin injection. Epidemiology here. Again, I'm not going to quiz you guys on this stuff, but I just find it interesting. 8 to 9 million worldwide. Type 2 is much, 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 much higher. Okay, this is more so of the acquired adult onset diabetes that we see a higher number here. These folks are typically born with it or develop it very early in life. Juvenile diabetes, it's called, because there's no lifestyle or dietary effects here. Usually, it is just a misfiring of the immune system. The incidence we see very high in Scandinavia, which is pretty interesting. In the U.S., about 25 per 100,000. We've seen these genes, HLA-DR 3 and 4, so that is part of MHC2 that has been noted to be a problem. Again, not the smoking gun, but has been associated with this disease. And we do see an upward trend in younger populations. So, yeah, a lot of good research to be done here. Autoimmune conditions on the whole are on the rise, and we got to figure out why. All right, so that is diabetes, and now we can roll on into celiacs. Remember, this is type 1 diabetes. This is T1DM. Oopsie, T1DM. I want to make that clear. Very different from adult onset. All right, celiac disease. This is if the diabetes was more so with the pancreas, this is more so dealing with the small intestine. This is an autoimmune enteropathy triggered by dietary gluten. Entero just means gut. Pathy means pathology. So an issue with the gut caused by autoimmunity. And that autoimmunity is caused by dietary gluten. What is gluten? A composite of wheat, rye, and barley proteins. So if you know anything about food production in general, that knocks out like 90% of things, right? The gluten's everywhere, absolutely everywhere. So, what's the deal here? We get exposure of this compound, and we'll get more into it in just a moment here, in genetically predisposed individuals, which activates these T cells that are reactive towards this compound. And that leads to destruction of intestinal villi, which are like the fingers that point into the lumen. And if I don't have that increased surface area, then I don't have good nutrient absorption. The fancy word for not good nutrient absorption is malabsorption. And then obviously if that tissue is deemed to be foreign and problematic, then you're going to have chronic inflammation with that area. So what is normally going on in my small intestine? It is lined with villi and microvilli to expand my absorptive surface area. So this right here, all in the teal is the small intestine, and the white is the large intestine. Okay? If I zoom on in, let's go crazy. In the walls of the small intestine, you have these projections that shoot up. Those are the villi. Those are the villi. And then on the villi, you have these little hairs. These are microvilli. So you see how I've increased surface area from this to now this. So now I can load all of this surface area with digestive enzymes, with absorptive enzymes, and that's exactly what I do. That's why the small intestine is as long as it is. I forget how long. I want to say, 22 feet? I forget. Whatever. That's okay. So that's the normal function. We have all that surface area to lay down extra digestive enzymes for proper absorption. And to boot, we also have this cool GALT that we've talked about a good chunk of this semester, honestly. So that's the GALT is a branch of that mucosal-associated lymphoid tissue, which is just dense networks of white blood cells maintaining tolerance in the area. So in this case, maintaining tolerance to food antigens and microbes. So in the innards, let's give me a purple here, right? In the submucosa of the intestinal wall, we have these lymphoid outposts. And those were the Peyer's patches. So a site of immune maturation is hanging out just in your small intestine, which is really good because we want to make sure that the cells that grow here aren't fighting like the hamburger that I just ate. Yeah, obviously I'm not a cow, so I shouldn't be reacting towards that. So let's be tolerant of food antigens. And obviously I have a lot of microbes hanging out in the gut that help me with vitamin synthesis, that help me with fiber breakdown. Obviously, I'm not a microbe. Those aren't me. But we need to be understanding that the friends in the gut are there to help. All right, so that's what's normally going on. Big fingers shooting in for surface area and absorption. And then my GALT that hopefully trains up tolerant and helpful immune cells. So in the case of this disease, we have a genetic component to it. Nearly all express this HLA combo. Again, not a smoking gun, but just a note that they present gluten antigens at a higher rate. So DQ, that's going to be MHC2. Some blend of these genes cause MHC2 to present gluten more often. So what is really occurring here in terms of the processing? So you have dietary gluten, wheat, rye, barley, whatever. It's in there. It's ubiquitous in most diets. Gluten contains gliadin, which if we just break down gluten, it's one of the persistent subdivisions of gluten. You have an enzyme that helps transport this broken down gluten. This is called tissue transglutamase, TTG. So break that down. A enzyme that moves gluten across tissue. So tissue trans across gluten mace or ace means enzyme. So the whole word there gives you what it does. So it attempts to uptake this gliadin, and when it does that, it does something called it deamidates it. Again, take biochemistry or organic chemistry rather, if you want to know what that means. All I'm concerned with is it removes a nitrogen group, and that makes this negative. Okay, so now we have this negative component here. Again, not super concerned with this. All this means now, what I'm after is the molecule has changed, and now it looks more inviting to antigen-presenting cells, especially those that are more apt to present gluten antigens. So what happens is this gliadin that's bound to this enzyme, this combo is now determined to be a problem. So the TTG gliadin combo, that's like everywhere. You have TTG all in your gut mucosa. So now that is deemed to be the problem child. And now that means I have my small intestine, almost all of it is recognized as foreign because this enzyme is everywhere. And if I'm eating gluten, then this enzyme combo will always be a problem. Okay, so that's the whole pathway. Gluten gets broken down into gliadin. Gliadin attempts to be uptook by this enzyme here. During the uptaking process, we make this combo, and this combo makes susceptible patients just absolutely increase it or causes this whole autoimmune reaction for whatever reason. So let's talk about what this leads to. If I have that enzyme everywhere and I'm eating gluten, then that combo is going to be ubiquitous. It's going to be all throughout my small intestine. So that means I have continuous inflammation, and that is going to damage the heck out of the mucosal lining, flattening the villi. Fancy word for that, villus atrophy, just the breakdown of those villi. Also increasing intestinal permeability. I'm breaking down the links between the cells that make up my small intestine. So I have leaky gut. This amplifies exposure to antigens, excuse me, and allows for the release of my microbiome into my vasculature too, which the microbiome is good for the gut, but it's not meant to go body-wide by any means. And if my villi are down, then I'm getting malabsorption of my necessary elements and vitamins. So just all around nuking the normal function and anatomy of your small intestine. So what is the immune failure here? Obviously my Tregs are lacking. My peripheral tolerance is not dealing with these autoreactive cells well. And my Peyer's patches, or just my T cell and B cell college in general, failed at saying, hey, gluten is not going to kill me. Gluten is just part of dietary antigens. Those are fine. I should have been able to tolerate that for whatever reason, maybe due to that genetic combo and some environmental issues. I do not. So now I have a reaction. What are the treatments? Pretty straightforward. If this is the problem, then get rid of this. This is in your tissue. You can't get rid of that. That is just part of your genetic makeup. You need you need TTG for proper gluten uptake. So if we just get rid of gliadin, which means getting rid of gluten, then we never make this combo and we don't have all the following issues. So a gluten-free diet would be necessary. And then while this was potentially causing villus atrophy or any type of malabsorption in general, nutritional supplementation would be great to offset that. And inflammation management, so like corticosteroids, can mitigate inflammation or any pain associated with this going on here. And then immunosuppressants would hopefully calm down any fired up autoreactive immune cells. But again, when I say treatments, this is not a cure. I'm just basically getting rid of the stimulus here. If we were to eat gluten 5 years later after doing this, there's a high likelihood that the response will be the same. So again, if your own tissue is the stimulus here, it's really hard to generate a quote-unquote cure. It's the same in this case. All right, and then to cap off with the epidemiology, this disease is actually pretty rare. I thought it was more prevalent than it was, but alas, we have the genetic link here. So again, not a smoking gun by any means, but something to note. And this is more predominant in females, 2-to-1, and a higher risk in type 1 diabetes mellitus patients. And I want to end on this super, I guess not cool, but let's say physiologically morbid, but curious and interesting note. Folks with one autoimmune condition have a high likelihood of having another autoimmune condition. Because if you think about it, if you have breakdown of central tolerance or breakdown of peripheral tolerance, both are usually occurring in autoimmune conditions and then lead to a autoreactive cell downstream, say in the pancreas. Well, if this is already broken, then it might lead to a autoreactive cell down another stream, say in the small intestine. Okay? So autoimmune conditions are highly likely to be combinant, to run with one another. Okay? So that would stink. You already have an issue that you're trying to fight, and oh dang, and you have another autoreactive condition that pops up. Okay? So a lot of the treatments for some of these autoimmune conditions are immunosuppressants. And then you give the patient immunosuppressants, and then that reveals another autoimmune condition they had that their immune system actually was keeping in control, but now can't because you're on immunosuppressants. So what a cyclical nonsense kind of issue this is, and maybe you're starting to understand why this is so complex and why it's so hard to treat and deal with. But yeah, so that's a cool note to end on. That is GI autoimmunity. Thank you for your attention, and let me know if you have any questions. Adios.